السلام عليكم ورحمة الله وبركاته. بسم الله الرحمن الرحيم. Are we done with the back propagation? Almost done. Almost done. Last time we talked about how we really do or implement back propagation, right? With matrices and vectors, right? You remember that? And inshallah today we'll continue talking a little bit about that, and then we'll talk about an important topic, which is how to initialize the parameters. Okay, and then we'll see if we have time to start a new session. Type. A very important concept in nowadays frameworks is called algorithmic differentiation. You saw that backpropagation depends a lot on differentiation, right? To get the derivatives, gradients, right? We need to be able to differentiate functions, right? Type. If we do that for very large networks, which means we have so many parameters, that will take a lot of time, right? And we saw last time that it doesn't take a lot of time because it ends up to be just multiplication between matrices and vectors. But still, how we can get the derivatives, the local derivatives, okay, so that we can chain these values. And whether we really need to, every time we build a network, we really need to implement how we get the derivatives ourselves or not. This is what we call algorithmic differentiation. So everything will be algorithmic, which means it will be already implemented for us. We don't need to re-implement the way that backpropagation is computed. What we actually really need to do is to specify what is the model in terms of the architecture of the model, how many parameters, how many hidden units per layer, how many layers, things like that. And we also define, of course, the loss function. Once you do these two things, once you define the model and the loss function, and of course you set the hyperparameters, then backpropagation can be done automatically. You don't need to do any, you don't need to define the way backpropagation actually works. How can we do that? That's what we will see in this slide. First thing, we will specify the order of the components. What do we mean by the order of the components? We'll specify how many layers, and that's how many hidden units in the first layer. And what is the activation function for the first layer? Then how many units for the second layer? And what's the activation function for the second layer? And so on. We will specify the order or the sequence of the components. So every component will know what the previous component is, how it is linked to the previous component, and how it is linked to the next one. Right? Type, why is that important? Not just because it's a network, because we are talking about backpropagation here. Why is that important for backpropagation? Because of the chain rule, right? Because the chain rule. Because for the chain rule, we need to know what is after us and what is before us, right? Right? Type two. And if you remember, what is the first step to do when we do it manually? If we want to compute backpropagation manually, if I gave you a function, and I told you compute the backpropagation derivatives, or compute the derivatives using backpropagation, what is the first thing to do? Draw what? The computational graph, right? If we specify the order of the components, it is like drawing the computational graph, right? So this is the computational graph. Of course, it's not drawn in the tool, but it is specified. خلاص, everything knows what is linked to and what is linked from. Yes, everything in the network. Yeah. Okay. Now we define the computational graph, right? If we define the sequence of the components. Now to do backpropagation, we need also to know how to compute for each component. What do we compute? What do we need for each component? the local derivative, right? The local derivative. So if each component knows how to compute its own derivative, then we know how to compute local derivatives. Type. Is that the case actually? And when we define a layer or when we define an activation function, it's the local derivative or the way that we compute the local derivative is not new, right? And if I define the sigmoid function, we know how to implement it. If we define a radio function, we know how to implement it. If we define a linear, the weighted sum, we know how to do the local derivative, right? So it can be implemented once, and that's it, right? Once we know, we say this is a sigmoid, it is already implemented for us. Okay, type. What is remaining? Okay, so that's, of course, these are examples. The radio knows, the linear function knows the derivative of the output with respect to input and derivative of the output with respect to also parameter. Then what remains is that we can compute the chain of the derivatives, right? And that's, of course, because we know the computational graph, we know what's next and what's before, we can do the chain of the derivatives. Okay, that's how we will get the final derivatives. So we don't need to do any computations ourselves. We just need to define how the components are linked together and the loss function. And even if the loss function is predefined, then we know how to compute the local derivative for the output values, right? Because that's before the loss function, right? So if it is already predefined, the derivative is already pre-implemented for us. And that's actually the case. Okay, and that's what we mean by algorithmic differentiation, that once we define these components, this tool, or whether it is PyTorch or TensorFlow or whatever, is doing the differentiation automatically for us. That's the main power of such tools, that we don't need to do this process ourselves or even re-implement it. Okay. Even if we have branches, by the way, yani sometimes in some networks, so far we don't have this because we have feed-forward networks, but sometimes we might have something like that. We might have, let's say that's a layer like that, and another layer like that. Okay. Sorry. No. Let's say that we have these weights here. I can say I will take also the output from these nodes and make it input to another architecture, another network. That's what we mean by branching. That can happen because now you know what? You know the Lego game? It's like Lego now. You put pieces somewhere together and the back propagation will be done, whatever you add. So you can do these branches. As long as there are no cycles, there will be no problem. It is straightforward. When it gets to cycles, there is a little bit of different handling. But other than that, you can do whatever you want. By what? Cycles. It's like saying that this is the output of this node will go back to be an input to another node behind me. Yeah. Okay. So as long as the graph is acyclic, which means that it doesn't have any cycles, then everything would be straightforward. Okay. So did you get the idea of algorithmic differentiation? So the differentiation is, once these components are pre-implemented, then we can connect them together in the way that we like. Actually, also, just emphasizing on what you said, we can have a network, two networks like that, and their output will be input to another network. As I told, it's like a Lego now, right? There are components, and these components are predefined, and you can just connect them together. Of course, you have to, for better performance, you need to really design by intuition. It's not just random. Okay, you must have an intuition on why you want to really do that. Okay, now let's switch to another topic, which is within the same, of course, session, which is about how to initialize the parameters. How to initialize the parameters. Why is that important? Why it's important to think about how to initialize the parameters of the network? Yes. Did you see any evidence for that before? What is the evidence? Yeah, so you saw that sometimes when we start from a point, okay, we might find the global minimum. In another point, we might not, right? So initialization is really critical, okay? So we don't want to initialize, or we hope that we will not start learning the model from a point that is very bad. Yes. Mm-hmm. Exactly. Yes, of course. Yes, of course. Not only better, but it can be faster also. Yes. Type. Usually in programming, in general, how do we initialize variables? In most cases, we initialize variables to zeros, right? Type. Why don't we do that here? Let's initialize. What are the parameters that we have? Weights and biases, right? Let's initialize this to zero, right? What happens if we do that? Huh? So what happens? Everything would be zero, right? Okay, so the network would be dead forever. خلاص. Okay, so you killed the network from the first instant. Okay, so of course we cannot do that. We cannot do that. If we initialize all the weights and biases to zeros, all the output, all the pre-activations and activation values would be zeros, خلاص, up to the end of the network. So we must have something that is better than that. Right. To do that, we will focus on this building block. So by the way, when I told you about this Lego, I meant actually the building blocks of the Lego, right? So we have now, it's like we have building blocks, and we are just connecting them together. So back here, if we consider this building block, that we have the biases and the weights, and we have the weighted average, or the linear function of them. This is the pre-activations, right? We saw this many times before, right? And the hidden units, of course, is the output of the activation function of the previous layer. So we saw these equations before. Now we want to see the effect of initialization on this building block. What will happen if we do initialization in some way, in some specific way, across the network? So the question here is, how do we initialize the biases and weights? And this is, as we just mentioned, is equivalent to choosing where in the space of the loss function, or the space of the model, where we start, which is, as we said, critical. To do it in a simple way, we will assume that we will set all the biases to zeros, but not weights. Okay, so we'll set the biases to zeros, and the weights we will set them, because we don't have specific way to do it, we will set them randomly. Okay, randomly, but not completely randomly. We will set them randomly based on a distribution, based on a probability distribution, which is a normal distribution. So we'll say that we will sample the values of the weights from a normal distribution with mean zero and some specific variance. So let's say, مثلا, if this variance is 1, then we expect that the values will be around 0. Okay, so around 0, because the mean is 0 here, and with specific variance. Okay, so it will be, if the variance is 1, it will be mostly between -2 and 2. That's the most cases. Okay, but they will not be zeros. Some of them will be zeros, but most of them will not be zeros. Okay, type. Now the question is, what will happen as we move through the network if the variance is very small or very large? We didn't say what the value of the variance can be, right? So I want now to think about the case when the variance is very small, what will happen across the network, and the case when the variance is very large, what will happen across the network. Let's think together. Okay. طيب. I will just do some. Okay, let's say that طبعا احنا we have here the rest of the network, we have here the rest of the network. Let's say that we are setting the weights in between these two layers. Okay, and let's say that this is the number of units here is dh, and the number of units here is dh prime. Okay. طيب. When we say the variance is very small, that means that the weights will be very small, right? Right? So the weights here, now I'm talking about the weights here, okay, between these two layers. Okay, because let's assume that we will set the variance for each weight matrix separately. And between every two layers, we can set the variance separate. Okay, but let's assume that in this specific case, all the variances will be very small. Okay, type. Now, the variances are very small, which means that the weights will be very small. Okay, type. What will happen to the pre-activation values here? Yani we have hidden units values here, right? Let's think about this node specifically. This node gets input from where? From all the nodes here, right? All the nodes here are connected to this node, right? But remember that the weights are very small. So what will happen to the pre-activation value? It will be smaller than whatever the pre-activation, the hidden unit values here, right? It will be very small, right? Type. How about this one? Same, right? Type. How about the next layer? It will be even smaller. But before the next layer, we didn't do the activation function, right? Okay. What happens with the activation function? يعني احنا we said that at that point the pre-activation will be small. The value will be very small, right? طيب, let's say that the activation function is radio. What will happen? It will remove the negative part and will keep only the positive part. Okay, so it's like getting the range of the values into half. Instead of having negative and positive, we just have positive. Okay, so two things are happening. The pre-activation values will be less, and after the activation function, it will be get to half the range. And the range, yani we can measure, we can think of the range as the variance of these values, right? Okay, طيب. How about the next layer? It will get smaller, right? Yeah, no, but here that's in general. But here we assume that the variance is very small everywhere. Okay, so with getting for the next layer, it will be even smaller, right? Next layer, smaller. As we move forward, it will get very small, right? Oh, what is smaller? The values of the pre-activations. Okay, so again, these weights are very small. Okay, the pre-activation values of this node will be will be smaller than the hidden units values, right? Here, and let's say that this is the hidden units values. Okay, and this is the pre-activation values. The pre-activation value here will be smaller than the hidden unit, right? Because the weights here are very small. And it will be halved because of the activation function. And then again, this process will continue. So it will get smaller and smaller as we move forward, right? Until we get to the output. خلاص? So pre-activations will likely have a smaller magnitude than the input, which is the previous hidden units. And then the radio will clip it less than 0. So the range of the hidden units will be even half of the pre-activation. This is what we just discussed. Okay? Type. So the magnitude is getting smaller and smaller as we progress through the network. خلاص? طيب. What happens if we have very large variance? It will get larger, right? It will get larger with the same logic. It will get larger over time. I mean, over layers as we move forward, right? The activation will keep it, but still it is larger than the previous, right? Because it's very the weights are very the variance is very large, weights are very large, so it will get larger. Okay, so that's similar thing. So the ReLU will have the range, but of course, if sigma square is large enough, the magnitude will still get large. Okay, now this is the summary of what we have discussed. The pre-activations can become so small or so large, right? You agree with me? That they cannot be represented by the finite precision floating point arithmetic. Yani it gets very, very small to the extent that we will get underflow, or very, very large to the extent that we get overflow. Okay, that can happen, right? Right. How about the backward pass? Really? Really? Okay. Remember what happened last time? And when we go backward, what do? We multiply by the weights. Okay. So it will get smaller and smaller and smaller again. So the same logic. So it gets smaller this in the forward pass, and even gets smaller in the backward pass. What will get smaller in this case? Yeah, in the forward pass, we compute the values, right? The activation values and the hidden units. Backward, we compute the derivatives. So the derivative will get smaller, smaller and smaller, right? Very small. And of course, in the case with very large variance, it will get larger. Still, we didn't finish. Okay, we didn't finish. So same logic applies to the backward pass. Now, the first case, when it gets very, very small, this is called the vanishing gradient problem. First of all, why is it a problem? And vanishing gradient means the gradient will be very, very, very small, right? And you know now, you can see now the logic. So why is that a problem? Why is that a problem? Yeah, so when the gradient is zero, what does that mean to us? No, it has nothing to do with error. The gradient, where do we use the gradient? No updates, exactly. Okay, well, the gradient determines the updates that we do. So why is that a problem? Because the gradient will be very small, which means that there will be no updates in the model. So we are stuck. The model will not be updated, and that's a big problem. Yes. Is that the case? Did it come to zero because we are reaching the global minimum? Most probably it's not. Okay, most probably it's not. Okay, it's because the weights are very small. Okay, but that's a good point. Yeah, it's zero. That might mean, but might mean in a normal case, not from what we just discussed. So this is called the vanishing gradient problem, and that's a big problem. If it happened, then the model is stuck, and you cannot actually continue training. You cannot continue training. Okay, right. The other one is called exploding gradient problem, right? Because the gradient will really be very large. Type, why is that a problem? The model will be unstable, and we will make big jumps. Okay, the gradient is very large, so we'll make big jumps. So the model is kind of going random across the space. So that would be also bad. So both cases are very bad. So we are not worried about which one is better. Both are bad. Okay. Yes. Question. Exactly. So as you see now, there are two extremes. So there must be somewhere in between that will give us good performance. Okay, and that's what we will see. Exactly. Okay. So this is showing it on a specific experiment. Let me explain first what this figure means. This axis is increasing is indicating the number of layers. Okay, so this is at layer number 1, this is at layer number 2, layer number 3, and so on until 50. Okay, and on the y-axis we are we are we are measuring the variance of the hidden units, which is like the values of the hidden units, okay, at each layer. So you can see with this value of the variance of the weights, what happens to the values of the hidden units? It's increasing, okay. As we move forward in the network, it is increasing. And by the way, if you look at the y-axis, it's log scale, so it's increasing a lot, exponentially actually. And you can think of it that way, right? It's we are multiplying by large numbers, so it's really exponentially increasing, okay. And this is also happening with this value. So these values are the values of the variance variable that we are talking about, okay. This is the variance that we use when we initialize the weights, okay. So when the variance is 1, we will get this effect. When the variance is 0.1, we get this effect. In the other way, if the variance is very small like that, you can see that effect, right? So what happens? The values are getting smaller, okay. Forget about the right side figure now, okay. We are only talking about the left side, which is the forward pass. خلاص? Do you understand now what's going on? طبعا if you look at the value 0.02, it's like stable. Is that a magic number? We'll see. Okay. طيب. What happens in the backward pass? You can see now the right side. Again, the x-axis is the layer, and the y-axis now is the derivative. It's the sigma square of the derivatives. Okay. So you can see the dotted line is the line from the forward pass, and the straight line is the continuation with the backward pass. And for example, you see this green one, this one, okay? That's the forward pass. And then when we get back, we will see that we will reach a very high derivative. Okay. On the other side, for the brown one, this one, that's the forward pass, and then the backward pass we are getting smaller. Okay. Type. Any question about that? Which of these cases are vanishing gradients and which of them are exploding gradients? 0.001 vanishing. Why? Because they are getting very small here, right? And this one also is vanishing. This one is vanishing also, right? Yeah. Yeah, it's not that much, but it's still vanishing. It's still getting smaller over time. How about this one? Exploding, and this one is exploding. Okay, so we have two cases of exploding here and two cases of vanishing gradients. That shows you that the choice of the variance that we use in initializing the weights is very critical. Okay, because it gets larger exponentially or it gets smaller exponentially. So we have to carefully set the variance in a specific way that we will discuss. Yes. Why it is that? Okay. You mean what is not changing? It's the variance is not changing. Okay, but the values themselves are different. يعني the variance across the layers is the same, but of course the values themselves are different. Okay, that doesn't mean a problem. Okay, yes. Because as we said, no, they are. This is log scale. This value is 10 to the power something, 5 or so. This is 10 to the power 100. Okay, these values are very large, are extremely large. Okay, at some point, very quickly, you will not be able to even represent these values with the fixed precision that we have. Yes. If it's increasing in this case, if it will increase, it will increase exponentially. So you will get very large number. Very large number. It's not around 0 or around 1. It's very large. okay, and in the opposite the same thing. Type. Okay. Now you can see now that there are very bad values for the variance and very relatively good, right? Which is this value, specific value. How can we set the variance so that we don't have either of these two problems? Now, if we go back to the figure that I started to do here, what is happening here? Let's say that we have a specific variance. Okay, let me get back here. Let's say that we have a specific variance here. Okay, when we get the weighted sum here, we get it from all of these neurons, right? Which means that the range of the value will be amplified by the number of these neurons, right? If I add more neurons in the previous layer, then the value will get increased, right? Right? Especially if the weights are in some range, and the weights are all in some range, then it is like we are magnifying the input values here by the number of nodes here, right? As this number of nodes increases, the effect will be higher on each of these nodes of the next layer, right? Right? Right. If I want to cancel out this effect, what should I do? Roughly, what's the simplest idea to do? Yani this is like we are multiplying the values by the number of nodes here, right? If then if to cancel it out, we can just divide by that number, right? We divide by that number. Is it that simple? We'll see. Okay, so if we want to be within the same range, that's the idea here. If we want to keep the values within the same range, then we need to cancel out this multiplication factor. Okay, so to cancel out this multiplication factor, we need to divide by the number of units in the previous layer. Okay, type. Remember that we also with the ReLU activation function we make the range half. I want to cancel this out. What should I do? Multiply by 2. Okay, multiplied by 2. So this is what we call he initialization, and he is not Hoa. Of course, it's a name of a person. Okay, so in he initialization, we want the variance of the hidden unit activations in layer k plus 1 to be the same as the variance of the previous layer. So to do that, we will set the variance of the weights to be 2 over the number of units in the previous layer. So that when we get the values from the number of nodes here, it's like we are canceling the effect that we are getting input from many units. Okay, so the range should be within, we should get we should get to a range that is within the same range of the input values. Okay, طبعا this is a rough idea. There is a proof for that, by the way. Okay, but this is roughly the main idea. Okay, right. This is in the forward pass, right? But in the backward pass, there is something, the same thing. In the backward pass, it's the opposite, right? And if we get back here, it's the number of of units in the next layer that will affect the derivatives, right? So what should we do? We divide by that number and also multiply by 2. Okay, so in the forward pass here, the variance should be 2 over the number of units in the next layer. Because the ReLU value, okay, yeah, it is the same concept, but instead of going forward, we are getting backward. The derivative will be multiplied because it's coming from multiple nodes from the previous layer. Okay, type. Now it's like these are two things, two rules. I want to make the variance of the weights between layer 8, layer k and layer k plus 1 to be like that, and I also want it to be like that. So can we do both? How? If these values are not the same, we cannot do both. If these values are the same, خلاص we are done. Yani if the number of units in layer k is exactly the same like number of units in layer k plus 1, خلاص we will set it to 2 divided by that number. If we have 10 here and 10 here, خلاص we will make the variance 2 over 10. Right? If they are not, then we have to find a solution. Okay? The simplest solution is to get the average. Is to assume that the number that we will divide by is the average of both. In that case, it will be 4 divided by the sum of them. Because the average is sum of them over 2, then it will be 4 divided by them. This is, of course, a heuristic. If it happens that the number of units is not the same between two layers. Okay? So summary, quick summary. What are we doing here? Why are we doing all of that? To initialize the parameters, right? And we said that we will set the biases to zeros, and we will initialize the weights by a normal distribution where the mean is 0 and the variance is what now? Is this. Okay, is this. And it has to be set per layer. That's why I said the variance can be different across layers, right? The variance of the weights, because it depends on the number of units before and after. Okay, the weights are between two layers, right? So this way, this is what we call he initialization. Now let's get back to this. You now know why it's 0.02, because in this experiment the number of hidden units was 100. It was fixed over all layers. Okay, so when the variance is 2 over 100, which is 0.02, then the variance of the derivatives will be stable. So we will not have the vanishing gradient problem, and we don't have the exploding gradient problem. And that's what we have here. Okay, is that clear? So you know now how did we get this 0.02? And this is showing it in practice that doing it that way, that derivatives will be stable. We will not have the two extremes. Of course, this is not exact. Yes. This one? Yes. So here we have, remember, this is like omega 1, omega 2, omega 3, right? Omega is the matrix of weights, right? Here we are talking about sigma square of omega 1. How to set sigma square of omega 1, sigma square of omega 2, and sigma square of omega 3. Okay. Yeah, we will be in the same range if we get just the average. This is like a heuristic, okay? Because it's like there are two rules that we want to comply to at the same time, and the two rules might be contradicting. So this is like a middle point. What is the point here? What are we doing? We are initializing the weights. Do we initialize the weights once, or we do it once in backward and once in forward? What is the meaning of what we are doing? It's once, right? خلاص, once. Once we will use it in the forward and we'll use it in the backward. طب how about the next iteration, the next step? Will we do another initialization? Okay, initialization means setting it in the beginning. Okay, so the first value of the weights will be controlled by the values of these variances. خلاص, done. Leave it بقى for training. خلاص. Of course not. Okay, the weights will be updated, right? By training. Training means updating the model. Okay, but to update the model, we have to start somewhere. This is where. Okay, so you see now the picture, the whole picture. I have a question. Oh no, by this way, we don't have to. It depends on what? It depends on the number of nodes. For example, for this specific example, the sigma for omega 1 will be 4 over 4 plus 3. And this one, 4 over 3 plus 2. And this one, 4 over 2 plus 4. Okay, in summary, we use this anyway. Okay, this one combines both. Good. Yeah. If the input is here, yeah, you can think of it as if it's a layer. Yes, it's the same thing. Yeah, because there is weights here, right? Yeah, there is a matrix here. Yeah. Okay. Very soon you will see that in the code. We'll see. Very soon, literally, in the next slide. Okay. Okay. Any questions? Right. Let's move on and see the code now. And when you see the code here, what I mean is that you will see code that will represent everything that we studied in the course so far. Okay, from the very beginning. How we actually do that using one of the frameworks that are used nowadays, and the most widely used one is PyTorch. So we'll see example that shows how to do all of this, to define a network, to initialize the parameters, to define the loss function, to choose the optimization algorithm, to choose initial learning rate and change it if we want, even to make random data and to train for, should be epochs, I think. That should be epochs. Okay, and train for 100 epochs. And this piece of the code is doing all of that. This is like, I think, if you remove the comments, I think this is like 20 lines of code that can do everything. If we just zoom in for a second, you can look at this part. Can you guess what are we doing here? We are actually designing the neural network here. We are saying this is the first layer with ReLU, second layer with ReLU, and then output. And for each, we are just defining by the name what it is doing. Okay, linear means it's the weighted sum, just the weighted sum, and then we add the activation function. Then weighted sum, and then we add the activation function. And to define a network, to define a layer, we just need to say how many neurons in the previous layer and how many neurons in that layer. Okay, so di, that's the input. Yeah, di is the input, which is 10. dk is the number of units in the layer, which is 40. And then dk, it's 40, 40. And then 45 for the output. No. How many hidden layers we have here? 2. Why is it 4? Okay, we are saying di is the input. So input is 10. And then 40. Okay, that's this part. And then we have another 40. That's this part. And then we have just 5 here. Okay, so we have input layer, we have output layer, we have 2 hidden layers. And that's all what we need to do. And even we can write it in single line, by the way. This is just for illustration here. This is just defining the network. And for example, this line is just defining or setting the loss function by just calling a function. Okay, it's already determined. Yeah, but now you understand these things, right? Okay, you understand this. And can you guess this? What is this? This is backpropagation. That's the 3 lectures that we spent so far is inside this function call, behind this function call. But now you understand how it works, I hope. Okay, instead of just calling a function called backward and you don't know what it is it's doing. This function actually is computing the gradients. This is the backward pass. Okay, so this is where backpropagation is implemented, or actually is implemented and computed. Okay, so you will see that inshallah very soon in the homework and in the projects. Inshallah. Any questions? Now I hope that when you use such framework, instead of just copying and pasting code as is, you understand every single line, what it is doing. And if you need to change something, you understand where to change and why you change and how to change. Okay? So this is backpropagation. Any questions? Type. This is just a side, but also related to what we are doing. I don't know if you heard the news or not. Did you hear the news last week? So for the first time in history, computer scientists were awarded Nobel Prizes, okay, in chemistry and in physics. In physics, this guy, if you remember in the first lecture, I showed you 3 guys who got the Turing Award. And I told you at the time that Turing Award means Nobel Prize in computer science. Now he actually got Nobel Prize. And he got it in physics. That was very surprising. And the reason that was stated by the organization is that he was inspired by physics, by concepts in physics, in making advancements to deep learning in particular. Okay? And on the other side, also these guys got Nobel Prize in chemistry, but for the reverse direction. They use deep learning to predict, I think, chemical structures or something like to discover chemical structures. Okay, so both are related to deep learning, which has a very important implication. I think that this is a very important topic, and I hope that you know that you are learning it in the right moment. Okay, so you need to really put a lot of effort in understanding it and learning it, and maybe some of us will win Nobel Prize. Now we have a hope at least. Okay, no one would think before that computer scientists. There's no field for Nobel Prize called computer science, and we thought that Turing Award this is the best. Now we can get Nobel Prize also. Okay, so you have to follow the news to get these things. So that's something good. But at the same time, I wanted also to talk about something that's not good, which is this one. I called it genocide and deep learning. Okay? The previous one was Nobel Prize and deep learning, I think. Yeah, and this one is genocide and deep learning. I don't know if you followed also the news or not, and you saw that in the news, what happened in Gaza, I think 2 days ago, in dawn, in very early morning. People were burned alive. Live. I don't know. I really don't know. And the reason that I titled this slide genocide and deep learning, because I think we will not be able to stop these things unless we own our will, and part of it is owning our technology. And the technology nowadays mostly is depending on deep learning, especially the AI tools. So that's another motivation for all of us to make sure that we really understand these things and master them, not just understanding for the exam. The exam will not benefit anyone, even you, by the way, not benefit you so much, more than really mastering it and understanding it so that we can use them for the benefit of our ummah. Okay, maybe we can, in the future, we can stop something like that instead of just watching it live. Okay. Okay. Now, new session. Any questions before we start this new session? Okay, طيب. Now we have like, okay, 10 minutes. The new session will be about measuring performance. Where are we in our course? We just finished talking about training, right? How to compute gradients and how to initialize the network before training, right? Now we want to know how good the model that is trained when we use it in reality. Okay? Yes. So we need to we want to have an idea of how the model will perform when we test it. Fine. We'll start with talking about a data set just to understand the concepts. We will use a data set called MNIST-1D. What is MNIST-1D? It's a variant of a data set that's very famous called MNIST dataset. MNIST dataset is a data set of handwritten digits. Okay, so every one of these is an example. Someone wrote a digit manually, and then we want to build a model that can recognize the digit. So it should recognize that this is 3, and this is 2, and this is 6, and so on. Okay, so this data set is for what type of problems? What is the problem? What's the type of the problem here? Classification. Is it binary classification? It's multi-class, of course. How many classes we have? 10, right? 10. Okay. Type. The input here is an image that shows the digit, written digit. Okay. But for simplicity, we had a variant of that data set that's called MNIST-1D. Instead of getting the input to be مثلا, let's say مثلا this is 100 pixels by 200 pixels, this is 200 by 200, this is 20,000 values. Okay, instead of having 20,000 inputs, okay, they had another much smaller data set where the input is just 40 numbers. So they converted the image into something that's 1D. So instead of having a complete digit, we have something like that to represent that this is a 0, something like that to represent that this is 1, and so on. Okay, and don't worry about the details here. But the idea is, instead of having a complete 2D image, we have just a vector of 40 numbers. And from the vector of 40 numbers, we want to discover what the original digit was. No, these are examples. These are training examples. What are the 40 numbers? The 40 numbers, can you see this one? Can you see the x value? These are the 40 values. يعني مثلا this is, let's say مثلا this is 0. Okay, let me change this. So let's say مثلا here x is 0. Here x is 2. Here x is 10. So 0, 2, and yes, the white dots, the x value of the white dots. Okay, so these are 40. Okay, yeah, they are manipulated. They are the original point, the original images were manipulated somehow so that we can get these 40 points. Okay, so this is called MNIST-1D dataset. Now, to understand the issues that we will talk about, we will assume that we will solve this problem using this specific network. We have 40 inputs, of course. We have 10 outputs, and we have 400 training examples per class. We have 10 classes, so the training examples will be 400 times 10. We'll have 4,000 training examples. Okay, we will have a model that has 2 hidden layers, 100 hidden units each. Okay, we will use SGD. What is SGD? Stochastic gradient descent with batch 100, a learning rate 0.1, and we will do 6,000 steps. What does that mean? Actually, I want you to tell me how many epochs here. Steps are iterations over batches, and every iteration is one batch. Okay, when we say steps, training steps, each step is one batch. Okay, so this is 6,000 steps, which means we are going over 6,000 batches, but we actually have the batch size is 100. So it's like 60 batches. How can we know do it? Okay, so the batch size is 100. The training examples is 4,000. So 4,000 over 100. This is the number of batches per epoch. Okay, and then you divide 6,000 by that number, will give you the number of epochs. Okay, you understand how to do it? Okay, right. Now let's look at the performance. So on the left side, the x-axis is the number of steps. So as we go through more data, we are measuring the percentage of error. What do you mean by the percentage of error? What is the error here? Remember, this is multi-class classification, right? So when the input is 3 and I say 4, this is an error. Okay, so percentage of error is the percentage of what percentage of mistakes I'm doing in the classification. Okay, type. Is that something expected, that as we going through more steps, the performance, the percentage of errors is decreasing? Yes, we are training. We are moving forward in training, right? We are training more. So when we train more, of course, the model is getting better. Okay. Of course, there is some fluctuation, of course, but overall the trend is that we are getting better. Okay. Up to this point, what's happening here? Zero error. What does that mean? Yani we are classifying perfectly. Okay. We are classifying all the training examples perfectly. That means that every single step here, we are measuring, we are doing inference for the network over all the examples, so that we can measure the percentage of the error. Because every point here, that means that we have a model now. Okay, so we can try that model we can test that model over all the training examples. Okay, that's the left side. The right side is exactly the same, except that the y-axis now, we are not measuring the percentage of error, we are measuring the loss. What is the difference between the loss and the percentage of error? Cross entropy. Okay, the multi-class cross entropy loss function. Okay, and it depends on what? Depends on the probability that the model will assign to the correct class, right? Okay, right. We can also see that the loss is increasing over time, right? Sorry, the loss is decreasing when we train more, right? And that's also expected. Type. Here we have zero error, but here we don't have zero loss, but we are very close to zero loss, right? Why is that? Why is actually the value of the loss is really different from the percentage of error? This is different. This is based on the probability, right? يعني we might get the correct label but with not high confidence. يعني I might assign 0.6 probability to the correct label. I got it correct because we maximize, remember? We get the label of the maximum probability. But the probability is 0.6, is not 1, is not close to 1. So there is a loss here. So the loss is different, of course. Okay? Type. Is that the real performance? And is that does that indicate actually the real performance of the model? Why not? Yeah, we have to check it on unseen data. Yes, and that's what we will see in the next lecture, inshallah. Okay. Assalamu alaikum wa rahmatullahi wa barakatuh.